Okay, this should be Chem42BBlake. The one I just filmed is up in there, so I'm going to finish that here in a little bit. We were on number 40, so let's go to number 41. Still on page 461. Nitrogen and oxygen gases react to form dinitrogen monoxide. What volume of O2 is needed to produce 34 liters of N2O? So we're going volume to volume, again for two gases, but you have to have the balanced chemical equation. Now, we're long past that, so you should know how to do it. So it's N2 plus O2, give me N2O. I have 1 times 2 is oxygen. There's an oxygen, so I need a 2 in front. That 2 means I have to have a 2 here. We have 34 liters N2. We need to know how much oxygen we're going to use. So, let's put what we're looking for. Equals V liters O2. V is equal to so many liters O2. What I know is I'm starting with 34 liters of N2O over 1. N2O. 34.0 actually. Now, just like before, on the last two examples, in case you missed it, we're going liters to moles to moles to liters. We have no information about what the pressure and temperature is and any other variables, so we have to assume it's the same. We could make it STP and convert to moles, and then to moles, and then to liters using 22.4 liters per mole both ways. If you do that, it looks like the one I showed you back here, where those just cancel out because they're inverses of one another. So these numbers, coefficients, we can use as liters as long as the conditions are the same. Nothing said about the conditions changing, so we have to assume that it's the same. And so we can go liters to liters directly. For every 2 liters of N2O, you have 1 liter of O2. These numbers mean liters also, as long as the conditions are the same. They don't even have to be at STP. Okay, so 2 liters of N2O consumes 1 liter of oxygen. And the answer is going to be 34 divided by 2, 17. By the way, I haven't been paying a lot of attention to these units canceling. This should be liters N2 right here. Get liters N2O, stick an L in there. So that cancels. So back here on these other ones, you know, these cancel. Okay, back on 39, these cancel. Okay, etc. So the same thing happens. So it should be 17 for this answer. 17 liters of O2. Okay, number 42, we've got to turn some pages here. More of the same. This time on 42, what we're doing on these ones is we're going volume to moles to moles to mass. We're going to liters to grams. And some other examples, we can go from grams to liters. Now, we can also, let me mention this because we're going to start doing this. We could use PV equals nRT to go directly to moles on some of these. I don't know if I'm going to do it on this one. But I can use PV equals nRT, jump directly to moles, and then go moles to grams. Okay, which is quicker a lot of the time. Or, if I'm going to grams, mass to moles, I could go to here, grams to moles, and then jump to PV equals nRT and immediately get any one of these variables, including volume. And I don't have to be at STP at all for that. So let's go on to the next one there. Ammonium nitrate, number 42, is a common ingredient in chemical fertilizers. You use the reaction shown, which they give you a reaction and balanced it, to calculate the mass of solid ammonium nitrate that must be used to obtain 0.1 liters of dinitrogen monoxide, the same stuff we had before. So we're going to go down to here and then convert to volume. Now let's see how I did it before, and I'll do it the same way this time. It looks like we did the whole thing, okay? We're going to volume to moles with 22.4 liters at STP to moles to mass. Okay, since they don't give you the conditions, you could put STP and PV equals nRT and get it and jump directly to there. But I'm going to do the whole thing. So we are looking for, if you write them like I do, X grams equals X grams NH4NO3. And X equals so many or other grams NH4NO3. So we are going to start with 0.10 liters over 1 of N2O over 1. Okay, so two significant figures because it's 1, 0. We are at STP, it says. That's an important thing to pay attention to. Since we are at STP already, the 22.4 liters routes is going to be faster. Okay, so let's go liters to moles to grams. So along the top, I think I have the right one here. Nope. Liters to moles. N2O is playing the role of A. To moles to B. Moles, and this time NH4NO3 is playing the role of B. And then moles to grams. NH4NO3. Okay, this goes here, this goes here, this goes here. So liters N2O goes here. Moles N2O goes here. Moles NH4NO3. Okay, so from the periodic table, that's this one. A mole of ammonium nitrate has a mass of what? Well, 68 times 3 is 48. We have 2 nitrogens at 14 apiece, that's 28. So 48 and 28 is 676, I think, plus 4 is 80. So about 80 grams. Now here's where I'm going to double up on my, well, no, I'll put this here. Now just in case I made a mistake, I'm going to check to make sure that's 80 on the next page. 79. 48. Okay, 79 or 80. I'm not sure which. You can use a calculator on it. That's not going to matter all that much. All right, now these numbers come from balanced chemical equation, and they are liters here, or moles. In this case, they're moles. And there's one of these, and one of those. And every mole of N2O from the periodic table. Nitrogen is 14 apiece, 2 of them is 28, plus 16 is apparently, oh, wait a minute, whoa, this is liters. This is liters. Liters, not periodic table. Liters, 22.4. Okay, now everything cancels. So 22.4 liters N2O cancels here. Moles N2O cancels here. Make sure you're putting your units in there and canceling them. You guys aren't doing that. Moles NH4NO3 cancels here, and this is what you're left with. Apparently the answer comes up to be 0.357 grams when you do that. Okay. All right, 43. Solid calcium carbonate is heated. They do this at concrete plants. There's a big one at Findlay on the way into Findlay on the highway out here. I think they do this. It's heated, decomposes to form solid calcium oxide and carbon dioxide. They use this to make concrete. How many liters of carbon dioxide will be produced at STP? Now, since we've got liters in STP, we can use 22.4 liters. We have this one in kilograms. Now we have to convert kilograms to grams, but we have kilograms to grams mass, to moles, to volume. We can use 22.4 liters because we're at STP. If we're not at STP, we can't use this 22.4 liters. Either have to convert, use the combined gas law like we have been doing, like we did in the last lab, or use PV equals nRT to get N. But this one's at STP, so just quicker to go through. Now this time I think we're going to have 5 terms because we want to end with V liters CO2, and V is equal to so many liters CO2. And we're starting with kilograms, so we have to do a kilograms to gram conversion. I can call those terms, and they're not terms. I do that all the time. Okay, so we have so many kilograms CaCO3. And every 1 kilogram is 1,000 grams for whatever it is, so I don't need to put that element in there. So first we got to get that in grams. Okay, and I have 2.38 kilograms. Okay, so that's going to cancel. But we're going mass to moles to volume. So next we want to go to moles, CaCO3, it's playing the role of A, to moles, CO2, moles, mass Ca3, kilograms, and then grams, to moles CaCO3, moles CO2, and then grams CO2. Over 1 mole CO2. This goes here, moles CaCO3. This goes here. In this case, grams CaCO3. Because if we cancel through, cancel your units, we've got it. I don't have my kilogram in there, sorry. Up here I have a kilogram. Okay, and just that part cancels kilogram here, leaving grams CaCO3. So grams CaCO3 cancels with grams and CaCO3 up here. And that step from the periodic table a mole of CaCO3, I want to say that's like 100. Okay, it's 100. It's 100 grams. Right? Or did I just say 90? 100. And then for moles to moles, from the balanced chemical equation, A, it's a mole of everything. So mole CaCO3 cancels. Okay, and then mole CO2 cancels. And from the periodic table, it's 40 or 44. Oh, no. No, I messed up. So I have to fix it. This was liters CO2. And that's 22.4 no matter what the gas is. Okay, so now you multiply everything to, 10,000 divided by 100 is 10. So it's 23.8 basically times 22.4, which would be about 500 roughly. 533, okay? And we'll do number 44 next.